Okay, we're going to take a look at number 9 in section 4.7. We're going to find the radius r and the height h of a cylindrical can of total surface area 110 square centimeters. Now, your number may be slightly different than this, whose volume is as large as possible. Okay, so this is a maximization problem, right? Optimization, we're going to maximize basically the volume of a can whose total surface area, in this case, is 110 square centimeters. So whatever you have for your surface area of your can will be done very similar to this. Now, one little trick they have in here is that they want you to express the numbers in exact form using symbolic notation. Fractions, symbolic notation might be radicals. So where needed. So that causes a little bit of difficulty, but we'll explain that when we get to that. So first of all, we've got a can. The base, the top and bottom of it is a circle, right? Radius r, and then the height of the can is h. So let V be the volume of the can, right? We're going to maximize the volume of this can. And what is the volume of a right circular cylinder? It's basically the area of the base times the height, right? Because it's a constant cross-sectional area. It's like a prism here. So it's just the base area times the height. The base area is a circle, radius r, that's pi r squared, times h. This is the formula for the volume of a right circular cylinder or cylindrical can. So notice we're going to maximize this, but it's a function of two variables, both r and h. We need to get it a function of one variable. So how do we do that? Well, there is a constraint, right? Notice we're told that the total surface area of the can is 110 square centimeters. So what is the surface area of this can? Well, we have the bottom and top, they're circles, right? Area of a circle is pi r squared. Okay, so we're looking at the exposed surfaces of this can, exterior, right? So we have the bottom and the top, those are two circles, radius r, so that's 2 times pi r squared, right? Pi r squared for the top, pi r squared for the bottom. So there's the area of the top and bottom. What about the sides? Well, if we take off the top and bottom and we sort of cut up the side of this can and then unfold it, it will unfold into a rectangle, right? The height will be h, the height of the can. What will the length be here? Well, it's the distance around the circle that is causing this length here, right? That's the circumference of the circle, which is pi times the diameter, or pi times 2 times the radius, right? Diameter being twice the radius, or 2 pi r. So this is the circumference of the circle, and that's the length of this rectangle. The area then of the sides of the can is just length times width, or height, length times height, 2 pi r times h, and that's what I have here. So this is the formula for the surface area of a cylindrical can, and we said that must be 110. So this is the constraint, okay? So I can solve for one of my two variables and then replace that up here and get volume as a function of one variable. And the easiest variable to solve for is obviously h. There's only one h. You don't want to solve for r because it's a quadratic function at r and it would be quite messy. So I can solve for h by first of all subtracting 2 pi r squared from both sides. And then I need to divide by the 2 pi r, right? And I'm going to divide everything by 2 pi r. So 110 divided by 2 pi r and 2 pi r squared divided by 2 pi r, right? I have to distribute that through over here. 110 divided by 2 is 55 over pi r. And then notice the 2 and the pi cancel and one of the r's cancel, and we just have minus r. So here's the simple formula for the height of our can given the radius. So I'm going to plug that in. In fact, you can see I've done that over here. I'm going to replace h right here, right, with this. And when I do so, right, here's my volume, okay? Before we go on there, I just want to talk about what is the range on r? What can r be? Okay, well, it's obviously not going to be, r and h are both non-negative. They can't be negative. And notice r itself can't be 0. And the problem with that is if r were 0, right, then notice this equation would not be valid, right? It has to be equal to 110. In other words, the surface area of our construction would not be 110. All right, if r is 0, you can see that here. These two expressions would be 0. Excuse me. So r has to be greater than 0. Is there any is just greater than 0? Can it be any, and is there any maximum value for r? Well, yeah. If you think about it, as r gets bigger and bigger, h is getting smaller and smaller. The extreme is h goes all the way to 0, And then what do we have? Instead of a cylindrical can, we just have a big circle, right, of radius r, right? If h goes smaller and smaller, the radius gets bigger and bigger, right? And then eventually h goes to 0, and we get that. In fact, if h goes to 0 in this equation, we just have 2 pi r squared is equal to 110, right? That's what I've done here. 2 pi r squared is equal to 110. And I can solve for r by dividing by 2 pi. 110 divided by 2 is 55. So I get 55 over pi, and then take the square root. So this is actually the maximum r can be, right? If h goes all the way to 0, this is the maximum r can be. And in that case, basically, we've got a circle which has no, which the volume is 0 for that. That's important to know. We'll talk about that here in a minute. But essentially, that means that r has to be greater than 0, but less than or equal to the square root of 5 over pi. And you can approximate that. This is about 4.18 is what this is. But again, I'm going to use exact values for the answers, right? They want exact values. So if this is the answer, that's what they want. Well, that's actually not the answer. We'll talk about in just a second. But again, symbolic, I'm going to leave it without rounding off anything. So let's go back here. Again, I plugged h in here. I'm going to distribute through here. All right. Pi r squared times this. The pi's cancel. R's, we have 1 r cancels. I got 55r. And then pi r squared times r is pi r cubed. Okay. And so how do we find the maximum of this volume? Well, we're going to need to find the critical points. And then because it's not technically a closed interval, r has to be positive. We don't have a left endpoint. We're going to use the first derivative test. We're going to do a sign check on the derivative. So let's find dV/dr. The derivative of 55r is 55. Derivative of pi r cubed, we bring the 3 down. I get 3 pi r squared, right? Subtract 1 from the power. So there's my derivative. Critical value, this is never undefined, but it is equal to 0 when 3 pi r squared is what? 55, right? 55 minus 55 would be 0. So when that is the case, I can solve for r now, dividing by 3 pi, and then taking the square root. Okay, so this is our critical point. So I do a sign check on dV/dr, right? We're going what? Everything greater than 0, so I'm not including 0, so I'm using parentheses here. Everything up to bracket, including what? The square root of 55 over pi, right? Which is about 4.18 if you use your calculator. And then our critical point is 55, square root of 55 divided by 3 pi. That's about 2.42. Okay, and you can do a check of the sign. Now, what's something between 0 and 2.42? 1, right? If I plug 1 into my derivative, what do I get? 55 minus 3 pi, 1 squared. 55 minus 3 pi. Well, 55 is much bigger than 3 pi. 3 pi is what? 3 times 3.14, 9 point something, right? So that's obviously positive. And if you plug in something between 2 and 2.42 and 4.18, like 3, if you plug in 3, then you'll get 27 pi, and 27 pi is actually bigger than 55. So this difference is going to be negative. But that's important because we've shown that by the first derivative test that we have a maximum at that. We have a local maximum, right? We're going from positive to negative. And in fact, for our situation, it has to be the maximum because we're restricted to this interval. We're increasing up to that point and then decreasing thereafter. So that has to be the maximum. So we're guaranteed to have a maximum at that value of r. Okay, but you don't need to know only r, you need to know the value of h, right? So how do you find the value of h? Well, the problem again is you have to express it in exact form. So I'm going to take this value of r, all right, that's where our maximum occurs, which again is about 2.42, but I'm going to use the exact value, and I'm going to replace r with this expression. Okay, gets a little nasty. So I'm just going to replace, right? There it is here, 55 pi r. I'm going to replace that with that minus r. So I'm just replacing that. Okay. And I mean, there's the exact value. So I don't know if Achieve will take that as your answer or not, but we can simplify this, and it's actually kind of instructive to do so. So it takes a little work. So first of all, what I'm going to do, I'm going to leave this alone, this 55 square root of 55 3 pi divided by 3 pi. I want to work on this. When I'm dividing by this fraction here, the square root of 55 over 3 pi, it's the same as multiplying by what? The reciprocal. And the reciprocal is the square root of 3 pi over 55. And I wrote the square root of 3 pi as the square root of 3 times the square root of pi over square root of 55, right? So I just broke that up. So again, dividing by this fraction is multiplying by its reciprocal. And then do you see what happens? I can do some simplifying, right? I got 55 really to the first power, and down here 55 to the 1/2 power. So when I subtract exponents, because I'm dividing 1 minus a half, I get a half. I get 55 to the 1/2 power. So we've got square root of 55. Here I've got pi to the first down here, pi to the 1/2. 1/2 minus 1 is negative 1/2. Pi to the negative 1/2 is 1 over the square root of pi, right? And then I've got my square root of 3. But if I put all this together, this gives me square root of 3 times 55 over pi. So it looks almost like this. Look, you wish the 3 was down here, huh? Well, then the difference would be 0. Well, that's not the case, all right? But I can make this look very similar to this by what? Multiplying top and bottom of under the radical by 3. So multiply the top by 3 and the bottom by 3. 3 over 3 is 1. And what happens? 3 times 3 is 9. 3 pi is 3 pi, and there's the 55, right? And then what can I do here? Well, the square root of 9 times 55, I can write as the square root of 9 times the square root of 55. And the square root of 9 is 3, right? So I get 3 times the square root of 55 over 3 pi. And look what happened. This is now exactly the same radical expression. So 3 of this radical minus 1 of this radical is 2 of this radical. So that's kind of not nice to simplify h down to that. So the maximum volume is going to occur. The maximum volume of this can will occur when the radius, again, is this quantity, which is about 2.4, and h is this. Notice it's just twice the value of r, so it's just double, right? That's when we're going to maximize the volume of this can when the height is twice the radius. Okay, there's one other question real quick we'll close with, and they kind of hinted at it already. Does there exists a cylinder of a given surface area, 110 square centimeters, and minimal total volume? Well, the answer is yes. Remember we talked about when if R gets bigger and bigger, H gets smaller and smaller. Eventually, H can go to 0. And what do we have? The surface area is still 110 because we basically have a circle. Right. Remember the value of R in that case when H goes to 0 was the square root of 55 over pi, right here. And we have a circle, and the area of that circle would be pi times the radius squared. If I square the square root of 55 over pi, I get 55 over pi times pi. It's just 55, right? That's the area of the circle. And it's got a top and a bottom. Both of those are 55 square centimeters. So the total is 110 centimeters combined. What's the volume of this circle? It's a two-dimensional object. The volume is 0, right? And you can even plug it back in. If you plug that value of R into our formula here, you'll get 0 for your volume. And so the answer is yes, you can have a minimal total volume, which is going to be 0. And then they have this interesting thing about the volume can become arbitrarily small. Well, that's obvious. Obviously, as R is approaching 0, we just said the volume is approaching 0. So that's obviously true. So it's checking the first option of the 3 that they have there. Okay, so this one was rather long and crazy, especially with trying to get the height expressed in a nice exact form. But hopefully it makes sense. Real important in this one is to make sure that you have, do the sign check, show the calculus that you indeed have a maximum. Okay, I hope this helps.